Science and Engineering Department, Pacific College of Engineering. I am going to start deadlock today. We will also study its characterization, prevention and avoidance. Now before I start with my topic, let me give you a very example of deadlock. Suppose there are two trains at a station. Now train T1 will not leave the station unless train T2 leaves, and train T2 will not leave the station unless train T1 leaves. So now they are interdependent and they are waiting endlessly for the other train to leave. Let me give you a very basic example through diagram. In multi-programming, what happens is, suppose this is a process P1 which is requesting resource R1. Now R1 is pre-allocated to process P2 which is requesting resource R2 which is pre-allocated to process P1. Now what happens is, P1 has resource R2 because the arrow goes from R2 to P1, which means R2 is allocated to P1 and P1 is requesting R1. Because the arrow goes from P1 to R1, that means this is requesting R1 which is preoccupied by P2. This process and resource diagram explains the deadlock condition. Now we will study the characterization of deadlock. Let us see how an operating system will consider deadlock occurrence. Now there are four conditions which, if occur simultaneously, deadlock is characterized. First one is mutual exclusion, in which sharing of resources is not possible between two processes. Second one is hold and wait. This is a very good example of hold and wait, in which P1 is holding resource R2 and waiting for R1. P2 is holding resource R1 and waiting for R2. Third one is non-preemption, in which breaking of any execution of process is not possible and we cannot allocate that particular resource to some other process. Fourth one is circular wait. This is again a very good example of circular wait, in which P1 is waiting for P2 to get completed and P2 is waiting for P1 to get completed, but they are waiting endlessly since R1 and R2 are not released. Now if we talk about prevention of deadlock, it is not possible because these four conditions may or may not occur sometimes. If we talk about write-only mode, there are cases in which we cannot allow two processes to write at the same time using the same resource. So mutual exclusion occurs, process has to wait for some other resource, and if it gets released, then again it will allocate it to that particular resource. That's why we cannot have deadlock prevention, but we can rather do deadlock avoidance. Using Bankers algorithm. In Bankers algorithm, consider processes such as P1, P2 and P3. Suppose there are three processes P0, P1, P2 and three resources such as A, B and C. Now, allocation means some amount of A, B and C are allocated to these processes. Max mean is the maximum requirement of A, B and C, and availability is availability of A, B and C at any particular instance. Let us consider that allocation is done in this way. As per Bankers algorithm, what we have to do is, we have to create a need table, which means maximum requirement minus allocation for these processes. Now, need table is maximum allocation for P1, P0, P1 and P2 for resources A, B and C. Now let's see, for P0 it is 0, 1, 1 and 2, 2, 3. So subtracting these we get 0, 1, 2. Here we get requirement is 1 and allocated is 2. So there is 0 requirement, 0 and 0. And in P2, 0. Let's say our availability is 1, 1, 1. Considering these cases. So now what we will do is we will have a loop for need is less than or equals to availability. When these conditions are satisfied, that particular process will execute and rest it will continue to next process. Now whenever execution of that particular process is done, the allocation of that particular resource will add it up to availability. Let's see, we have 1, 1 and 1 instances of A, B and C. Here process P0 requires 2, 1 and 2 for A, B, C, so this is not possible. This condition is not satisfied. Next we go for P1. Here in P1 it requires 0, 0, 0 resources. So P0 will get completed first. P1 will get completed first. Now whatever resources are allocated to this process will add into this. So we now have 3, 4 and 6 resources. Now let's compare this with P2. Obviously P2 is satisfying this condition. So next it will execute P2. And now when P2 is completed, allocated resource will get added up to this. So now we will be having 3 plus 4, 7, 4 plus 2, 6 and 6 plus 3, 9 resources of A, B and C which will add it up. Now let's check the condition for P2. It is satisfying the condition. So last one will be P0. In this way we can avoid deadlock by using this particular algorithm, and each process will complete it in some particular time. Thank you for watching this video. Please like, subscribe and